Greetings, gang. Welcome to Chapter 3 and Kinematics, or the study of how things move. Recall that we're actually moving really fast right here, right now. The Earth is rotating, right, spinning, but it's also revolving around the Sun. The Sun is flying around the Milky Way galaxy. The Milky Way is hurtling through space, and so on. But relative to each other, right, relative to the chair you're sitting in and the room you're in, you're not moving very fast. If we say your car is moving at 100 kilometers per hour, what is it moving 100 kilometers per hour relative to? The road, the earth, right? Let's take a closer look at speed, velocity, and acceleration. We already mentioned that speed is a scalar, right? Speed does not have direction, and so it's not a vector, right? Your speedometer in your car tells you that you're moving at 100 kilometers per hour. That means your speed is going to tell you that you're going to move 100 kilometers in 1 hour, right? Or it's going to tell you a distance that you travel per unit of time. Sometimes we write that as change in position over change in time or something like that, right? Distance over time, however you want to say it. Now, we don't use miles in science, of course, and so usually we use something like meters per second, kilometers per hour sometimes, it just depends, right? For our intents and purposes, most often we're going to use meters per second, because we're going to be talking about small distances and small units of time. Now, some vocabulary for you. The average speed. The average speed is going to be the total distance traveled divided by the total time elapsed. What that means is you may speed up and slow down over the course of something. Let's say that you run the 100-meter dash, for example, right? Okay? If you run the 100-meter dash, the total distance that you travel is going to be 100 meters. Let's say you run the 100-meter dash in 10 seconds. Now, along the way, you were probably going really fast right out of the blocks, right? And then over the course of time, you probably slowed down a little bit, right? And then maybe sped up again, who knows? But your speed was not constant throughout. And so your average speed, you just take the total distance that you traveled divided by the total time, and you can see 100 divided by 10 is very clearly 10 meters per second. That's your average speed, right? Now, your average speed is distant from your instantaneous speed. Your instantaneous speed is how fast you're going at one instant in time. If you look at your speedometer, for example, that's going to tell you what your instantaneous speed is at the moment that you glance at it, right? Now, velocity is what you get when you give an instantaneous speed a direction. Thus, velocity is a vector quantity. And sometimes you write vectors like this, like velocity with a hat to show that it's a vector, okay? So we're going to say that velocity is change in position divided by change in time, right? That's like your final position minus your initial position divided by your change in time, which is like your final time minus your initial time, something like that, okay? Acceleration is a change in velocity. And so that's like your final velocity minus your initial velocity divided by your change in time. Final time minus initial time. I'm not going to write that again. You can accelerate something by changing either the magnitude or the direction of the velocity. Obviously, if you're changing just the direction, the number may not be very big, right? because you're not actually changing your speed. But if there's a change in velocity, it can occur quickly or slowly, and that again means that the time is important, right? If we want to quantify a change in magnitude of velocity, we say the acceleration is the change in velocity per unit time, like so. Note that the acceleration of velocity over time is obviously velocity, so we got meters per second here, right? Velocity is meters per second, or meters per second squared, like we mentioned before. Now, I'm going to take this equation here, and I just want to show you what I mean, which one in particular I'm talking about here. So acceleration is final velocity minus initial velocity divided by time. I'm going to rearrange by multiplying time to this side and then adding the initial velocity. So acceleration times time is equal to final velocity minus initial velocity. I'm going to add this to the other side, and I'm just going to say initial velocity plus acceleration times time is equal to final velocity, or final velocity is initial velocity plus acceleration times time. I'm going to put this over here in the corner. Actually, I'll put it over here. Initial velocity, let's write it this way. Final velocity is equal to initial velocity plus acceleration times time. We'll call that equation 1. We'll come back to this one later, okay? Now, what does this mean? This means that if you start with some initial velocity and you speed up a little bit over time, you may go faster, right? Your final velocity is your initial velocity plus how much ever you sped up or slowed down. That's all that means. Recall that if you're moving while accelerating, either speeding up or slowing down, then you can describe the distance you traveled by your average velocity and the time elapsed. That was just the definition or the statement of average velocity, right, or average speed. If you're moving with constant acceleration, because some constant force like gravity, for example, is accelerating you, then your velocity will change at a constant rate. Thus, your average velocity is the average of the final and initial velocities, right? So let's say your average velocity is like your final velocity plus your initial velocity divided by 2. It's true, right? And therefore, the distance that you travel during a time interval should be the average velocity times time, right? So we're going to say your position at some time t is your average velocity times time. That's going to be final velocity plus initial velocity divided by 2 times time. Okay, let's reconsider equation 1 here for a second. Okay? Now, before we start tinkering around with this anymore, very quickly, the equations are called equations because anything that's to the left of the equal sign equals what's on the right of the equal sign. This side equals that side, right? It's like saying 1 equals 1. That is a true statement, right? Now, if you want to change an equation or manipulate it in any way, shape, or form, you have to do the same thing to one side as you do to the other. So if I added 2 to both sides, it becomes 3 equals 3. That's still a true statement, right? Okay. Now, let's let's go back to equation 1, this thing. I'm going to put this other equation here off to the side, the one that we just wrote. V final plus V initial over 2 times time. We'll call that equation 2 maybe. Okay, let's take equation 1. We're going to add the initial velocity to both sides. So we're going to have V initial plus V final is equal to 2 V initial plus acceleration times time. I just took equation 1 and added VI to both sides. Okay? Now, I'm going to multiply both sides by delta t over 2. I know that's going to sound a little funny, but you got to just bear with me here for 1 second, okay? This is actually going somewhere. Okay, so we got initial velocity plus final velocity over, oops, that's supposed to be final, over 2 times delta t, right? Or time, you know what, let's just remove the delta. Doesn't really mean, it just means change. Okay? So I took this and I multiplied it by delta t over 2. We ended up with this term. And then we're going to do the same thing on this side. Okay. Delta t over 2 times 2vi. Obviously we're going to get 2 over 2. vi, so we've got vi times t, right? And then we got at times delta t over 2. We've got 1/2, right? 1 over 2 times a times t squared, right? Now, let's look very closely. We said before this was our average velocity, right? The initial velocity plus final velocity over 2. So this is v average times time is equal to, now 2 over 2, that's just 1. So initial velocity times time plus 1/2 at squared. Right? Recall that the average velocity times time is your position after a time interval t has elapsed. Thus, this equation here is really telling us that our position as a function of time is our initial velocity times time plus 1/2 times our acceleration times time squared. Now we sort of missed one important piece of information, and I'm going to add it here. Your position as a function of time is equal to your starting position plus your initial velocity times time plus 1/2 times your acceleration times time squared. This piece is your starting position. That's important because let's say that your friend challenges you to a foot race and you can both accelerate at the same rate, right? You're both just as fast, you're both starting with the same velocity out of the blocks, but if you let them have a 5-meter head start, they're going to win the race, right? So your initial position is important. So, let's look at another case here. Let's say you're going to just let something fall. If it's falling from rest, then your initial velocity is 0, right? If you're going to call the starting position 0, right, that's also 0. And so the height, or the vertical position of something, is just 1/2 times the acceleration times time squared in that case, right? This is for simple free fall. Now all we need to know is the acceleration of a falling object. First of all, what's causing the acceleration? Obviously it's gravity, right? Usually we write gravity as a lowercase g. Now, because We're here near the surface of the Earth. G is approximately 10 meters per second squared. This is the way you would write it. You would write it as 10 if you had one significant figure, right? If you had two significant figures, you would write it as 9.8 meters per second squared. If you had three, you'd write it as 9.81 meters per second squared, and so on. You're not going to need to write more than probably three in this class. Most of the time you can use 10 or 9.8 or 9.81 just to make things simple. Therefore, perhaps the best way to write a free fall equation is your height as a function of time is 1/2 gt squared, where g is our friend the acceleration due to gravity. Now, as an object falls, obviously it's going to fall faster and faster, right? And if we remember the definition of acceleration, your final velocity, your final velocity is your initial velocity plus acceleration times time, right? Thus, if something falls from rest, meaning a zero initial velocity, you can tell how fast it's going to be falling, right? So if you're falling from rest, right, if you're taking some object and just dropping it, so it has a zero initial velocity, then you can basically reduce this equation to the final velocity is your acceleration, which of course is g for gravity, times time. Now if we said g was 10 meters per second, after 1 second, time 1, you would be falling at 10 meters per second. After 2 seconds, you would be falling at 20 meters per second. After 3 seconds, you'd be falling at 30 meters per second, and so on, right? Okay, quick check for understanding. If you have an airplane, here's my awesome drawing of an airplane, okay? This airplane is moving at a velocity of 80 kilometers per hour, and it encounters a crosswind of 60 kilometers per hour. How fast is it actually moving? Well, in order to do that, you would have to invoke the Pythagorean theorem, right? This is 60, this is 80, and you can do the math yourself to figure out that this is 100. Now, really quickly, if this crosswind, instead of being 60 kilometers per hour, if this was 80 kilometers per hour, you would have a different triangle, right? This would be 80, this would be 80, and then in order to figure this out, (80 squared plus 80 squared square root), that puts this closer to 113. Okay, finally, let's say you are running with a velocity of about 4 meters per second. Not that fast, not that slow, right? Okay, now let's say that rain is falling down, right? With a velocity of 4 meters per second also. Relative to you, what does it feel like, the angle that the raindrops are coming at you with? Well, you're moving this way with 4 meters per second. They're moving down here at 4 meters per second. These are equal, right? This side is as big as this side. That means this is 45 meters. Halfway in between 0 and I hope you've enjoyed this lecture video. I'll see you next time for Chapter 4.